Welcome to another video explaining the universe using the particle model. My name is Bob D. Hilster and I am your particle model guru. Today's video is the third video where I'm covering my book, Gravity is Not Free. This is part two. Part two is all about my work on gravity for about 10 years. And in particular, I'm going to cover the experiment and the equation. Now, Gravity is Not Free is the title of the book written by myself. It spans a period from the early 1990s when David got started to the spring of 2015 where I switched and started working on the particle model, including light and the rest of it. There are 4 parts to the book. The first video I just did an overview. The second video was on Dave, part 1 Dave. This is on part 2, my section in the book. And there are actually 14 chapters in this book. I'm not going to make 14 videos. I've decided to break it into 3 groups. This is the experiment and the equation. The next one will be on the speed of gravity, which I consider a critical point. And the third one will be on an experiment done by Majorana and the calculations. So let's talk about the experiment. One of the videos, I covered it fairly well, but this is a brief overview. Dr. Karazani suggested that this experiment could prove that Lesage's theory of pushing, where the particles would push the ball towards the smaller block, would prove that Lesage's theory was correct. Of course, the standard answer is that the ball ought to move towards the larger mass. So he was expecting the ball to move this way when he the experiment was done. Well, the first thing I did, because when David asked me to help with it, was to develop an equation because I had to know what to really expect. And so I developed this equation down here, which is a 2-dimensional equation, but I was going to compare it to Newton's equation, because with Newton's equation, you expect the ball to go to the larger mass. To do that calculation, I broke each block into 4 perfect squares and calculated the force from the center of gravity of this to the ball, from the center of gravity here to the ball, from the center of gravity here to the ball. That gave me 12 different equations, and that's what the summation represents. A equals 1 to 12, and each position has an angle. And this is Newton's equation. You sum all 12 up and you get the force on the ball. What I would do is I would place the ball here and do the calculation, and I would place it all different places, and like here, and do the calculation for each position. So I calculate the force at each position that the ball could be in. Now the 2D pushing model, I'm not going to explain this whole one yet, except that n is the number of G1 particles coming into the model from all directions. F sub G1 is the force per G1 in newtons per G1, which gives me a force in newtons. And I start with angle 0, which is up here, and I go around 360 degrees calculating the value for each position of the ball. Went through all that. Well, the result was I got this curve for those 2-dimensional equations. The pink curve is Newton's curve, which I call the pushing force, or pulling force, and then that's the pink one, and the pushing force was from my 2-dimensional equation. And now they're close, but they're not exact. And I realized that if you really want a better answer, you're going to have to do three-dimensional equation. So I did a three-dimensional curve. You'll notice that inside here, from this summation to the cosine of A, is the same as the two-dimensional one, and going around 360 degrees in the horizontal plane. But besides that, I added this summation, selecting 180 planes. With 180 planes and 360 degrees in each plane, you cover all the directions of forces three-dimensionally, and you have to add the cosine of the angle of the plane. And this is the result. Much closer, much better, indicating the ball was going to move the same way, whether it was a pull or a push. It was going to move the same way. Well, the results, as Carasani was wrong. His prediction was wrong. My prediction was that it would move the same way. Second, when we tried to set up this experiment, this is showing a part of the experiment. There's a big lead bar here, small ball here. It's not a ball, but a rectangular shaped piece of lead. And we would stabilize it and then watch it move, but it would never really move. Once it was stable, it never went one way or the other. So we had to push it. We pushed it, took a video of it, and I analyzed the videos to see if there was any acceleration in it. And yeah, we got some results, but basically the experiment was a failure. We went to the NPA 2007. David, myself, and a friend, Jeff Hunter, who did some of the mechanics, all wrote part of the paper, and I presented it at the NPA 2007, which I believe that was in Storrs, Connecticut, at the university there. You can find this paper at this link. Its title is Gravity Experiment 1. Well, the experiment may have been a failure, but I considered the equation to be a success. It was remarkable to me that those two equations that were so different would give you the same curve. So now I'm going to talk about the equation and how you develop that equation. And I'm going to talk about a one-body equation that has a single reduction in the equation, then a two-body using the Earth and Moon. And in the particle model, you get an equation for the force on the Earth and a separate one for the force on the Moon. And each of them has a double reduction in it. And then a three-body model, Sun, Earth, and Moon. Again, each object gets its own force equation, and each equation has a triple reduction. It includes all three objects in it as a matter of how it's developed. So let's look at the one-body model, just the Earth, and what we're really trying to do here is develop this equation that the net force at this point is divided by the mass of the Earth is going to give me the gravitational acceleration of this point. Now I can move it anywhere I want in terms of distance and calculate that as well. But this is the model. We assume always that the number of G1s coming in is the same all around. And then as this passes through, a certain percent is going to interact, hit, and get lost and scatter. And what leaves and comes out of the Earth at this point is this value. It's n minus that, which turns out to be n times 1 minus the percent lost, the percent that pushes. And the net equation is the sum of these two. The forces in this is a greater, this is obviously a smaller number, this is a greater number, so it's this force minus this force, and that's exactly what I call the basic equation. The net force, in this case, the net number of G1 particles pushing on that point is this expression. that 2D equation is developed. Remember, A equals 1 to, I take 360. So you've got to take this as your point of interest, and there are other angles. There's other directions coming right through here or coming through here. And so you start here with this being 0 angle, and you go all the way around calculating all 360 forces, and that's where you get the basic equation surrounded by the sum. Now, to get the force, I assumed that there was an average force per particle when it hit. So you take the number of particles that are times this force per particle gives you newtons. This is newtons per g1 particle. So so you take the basic equation, you surround it with the summation, you get the net force when you include this term. Now, this percent reduction is just a percentage number, right? It's non-dimensional, but I assume that it was proportional to the mass of the path. Each path, in this case 1 degree, is kind of a small wedge here that has a certain amount of mass assigned to that path. And that's what I calculated, was how much mass was in that path. And I said the percent was proportional to that. But what's the proportion? Well, this is the constant of proportionality, which I call the interaction factor, which makes it an equation. And these are 2 of the parameters, the virtual constants that I use in the equation. And so you now have a 2D equation, and you could also do a 3-dimensional one. With an ideal Earth, is all going to come out the same, 2-dimensional or 3. Well, here's the 2-body model. Here's the Earth, and here's the Moon, and here's all this stuff going through, and here's the force equation on the Moon. And to get the force on the Moon, which is over here, this equation, you track the loss through the Earth, giving you this, and then this enters the Moon, and you have loss through the Moon, and the net result is n minus this, and then you do it around 360 degrees. This is a 2D equation for a 2-body model. The force on the Earth is the other way around. You follow n this way, you lose this many going through, this many leave the Moon, and then you end up with this many being lost in the Earth, and the net force is this minus this. And that's what you have here in the basic equation, and you surround it by the summation. That's the 2-body model. Notice in the 2-body model there are 2 reductions. There's a double reduction. It's that small double reduction that adds just a little bit more loss than a Newton equation could give you. But let's take a look at this, the basic equation again. This is for the Moon. If you simplify this equation, you get this, where you end up with the number of G1 particles times the percent through the Earth and the Moon. But even though these are in opposite places in the equation, for the Earth it's the other way around. You get this loss first, then that. Mathematically, these are identical. This is identical, which tells you the force on the Moon and the Earth are equal. The math is good. When you do this simplification, the math is good. But the physics is lost. When you eliminate this n and this n from the term to get this, you've eliminated the source. So you have a net force with no source. And physically, that's not right. You can't have, You eliminate a battery from the circuit. You don't have current anymore. You got to keep the battery there. This is a good physical equation. This is just math. The problem is when people use simplified equations like this and move on further using only the net, and they've lost the source, they've lost the physical integrity of what's going on. The second point is Newton doesn't give you two equations. Newton only gives you one. And generally you're asked to assume that the Earth is stationary and the force here is the force on the moon, and it's the net force. What this tells me about this equation is that half of this force is on the Earth and half of it is on the moon, if this is a true net force. And if these equations give the same answer, then this force plus this force equals that force, and they're equal. So that's an interesting point about reducing equations. Be careful when you reduce equations. Now here's the three-body model: Sun, Earth, and Moon. And I'm not going to go through the equations except so you can see that the force on the moon is equal to the number coming in minus this, and there's a triple reduction here in this equation. Force on the sun is this term minus this, and there's a triple reduction here. There's an interesting point about the Earth that's in between. Of course, these are not always lined up in neat positions, and as you move the Earth and the moon around, you're going to get all kinds of strange modifications of what these things look like. But on the Earth, you have a force pushing this way, and you have a force pushing that way. These are different. This is the percent lost in the sun and then the Earth. This is percent lost on the moon than the Earth. The percent lost on the sun is greater than the moon. Therefore, this is a smaller number. Therefore, the net force is this way. But in fact, there's a force on the Earth towards this way and a force this way. That's the three-body model. Okay, well, now I'm going to compare this equation to the circuit equations. I've done a number of videos on circuits. This is, I think, the first one. And you can find it at this link, and I describe this circuit and how the model works in this case. The battery is emitting. In this case, I use the word 90 of them out, and so that B is equal to the number coming in, A coming in plus 90, and I'm assuming A here is 10,000, so this is plus 90, and then C is equal to the number coming in minus the loss here, and you go around that, and these are all the equations, and you'll notice that I have E, this is E up here, is equal to D, the coming in, minus 1 minus, this is the percent, PR1 is the, or PR3 is the percent lost through, this is through resistor 1, the loss through resistor 2, and this is the same formula as gravity, except that the percent lost is equal to a constant of proportionality times the resistance, where in gravity it's the percent loss is equal to the constant of proportionality times the mass. Very similar equations, simple algebra, and but you use it a little bit differently. In gravity, N is coming at the point of interest from all directions. In this case, the G1 particles are flowing through the circuit like a fire hose, a massive amount of G1s flowing around. And so the system itself is different. This is almost just a linear equation. You don't need to sum this in the plane. These are just a series of linear algebraic equations. whereas gravity, you could do a two-dimensional or three-dimensional equation, but the basic idea is the same. Because the system is different, because that's different, I expect that I sub f for the circuit will be different than I sub f of the gravity equations. Well, my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will talk about the speed of gravity. Thank you for your attention.